Yiru is now currently working towards a PhD degree in marine meteorology at Nanjing University of Information Science and Technology in Nanjing in China. Her research interests include the sea surface wind field and sea ice remote sensing through multipolarization and compact polarimetric synthetic aperture radar.
Hello, everyone. Can you see my screen?
Yes, we can hear you and we can see your screen. Perfect.
Good afternoon, everyone. Today, my topic is about Arctic sea ice and open water classification from Spaceborne polarimetric synthetic aperture radar. Satellite observations have revealed the remarkable decline trend in Arctic sea ice extent, thickness, and volume, predominantly caused by strong natural variability in the coupled ice ocean atmosphere system and anthropogenic carbon dioxide emissions. The decreases in sea ice cover in Arctic will lead to more frequent polar navigation as well as offshore oil and gas exploration.
Yiru, sorry to interrupt. Can you please go on full screen or like do presentation mode for your we see? Oh. But it's okay if not. Like
it'll be. Do you see the bar along the bottom? There's the little grayed out one. 3 over from that. That kind of looks like it has a little stick coming out the bottom.
Yeah, you can press the F5 to show the full screen of your presentation.
Sorry about that.
Perfect. Thank you so much.
Capable of observing sea ice at high resolution and wide swaths, Spaceborne C-band SARs have proven to be valuable tools for local and regional sea ice analysis and monitoring. SAR images have been widely used to discriminate sea ice and open water based on statistical approaches and machine learning models. Although these methods are successful in certain conditions, they still face major challenges in order to obtain more accurate ice water classification results, especially at the ice water boundary and for small scale features within pack ice. A great number of high quality samples are indispensable for these supervised classification algorithms to develop and validate models. Ordinarily, the ice water segmentation reference based on 2 component activities: visual interpretation of SAR images and sea ice charts from operational ice service divisions. However, these 2 methods may lead to level errors due to the subjective analysis by the operator, as well as time interval and spatial resolution discrepancies between SAR images and the ice charts. Fully polarimetric SAR data contain abundant polarization information and have potential to be used for distinguishing sea ice from open water. Polarimetric features are beneficial for ice water classification due to their relevance to different scattering mechanisms. So in this study, we aim to develop an automatic sea ice and open water classification algorithm for Spaceborne polarimetric SAR. We collected a total of 869 RADARSAT-2 5-protocol SAR images from October 2008 to September 2019. These images were selected to cover various sea states and open water under different wind and sea conditions. The following figure is the geographic locations of RADARSAT-2 SAR images. For the generation of training samples, the unsupervised HH alpha Wishart classifier, which is the synthesis of the unsupervised target decomposition classifier, and the supervised Wishart classifier is used to automatically segment corpuscular star images. This classifier is linked to physical scattering properties. And figure C is the segmentation results using the HH alpha Wishart classifier. Based on this result, we further inspect HH HV star images and the associated poly-RGB image, assigning each pixel to a specific type. Finally, more than 1,300,000 level samples are generated. The percentages of sea ice and open water samples are almost the same for model training and validation. Moreover, the number of samples do not vary significantly with incidence angle except for the smallest incidence beam. For feature extraction, we extract 33 polarimetric features estimated from scattering matrix elements and eigen decomposition parameters of the coherence matrix, as well as 18 texture features using the gray level co-occurrence matrix. The random forest model is implemented for the ice water classification, which integrates a number of decision trees into a forest, and each tree is constructed and trained using random subsets of the data set and random subsets of the features. The majority voting of the trees is used as the final decision of the random forest model, so it can generate more accurate classification results than conventional decision tree models. Besides, in order to eliminate feature redundancy and reduce model complexity, we combine the recursive feature elimination method with the random forest model to select the most representative features for ice water classification. To demonstrate the importance of polarimetric features for ice water classification, we designed 3 experiments with different model inputs. The first experiment used 3 image features as the model input, namely HH HV-polarized, radar backscattering, and incidence angle. The second experiment take the additional texture features as the model input, and the third experiment use the additional polarization features as model input. Based on the RFE method, for the third experiment, 14 polarimetric features and 3 image features are chosen, among which polarization difference is found to be the foremost polarimetric parameter with the highest ranking. For the second experiment, 11 texture features and 3 image features are chosen. To evaluate the method proposed in this study, we conduct both statistical validation and case-by-case comparisons. The statistical results show that compared to the other 2 experiments, our method improved ice water classification accuracy by 5 to 10%, with the overall accuracy of about 99% and the Kappa coefficient of 0.999. These results suggest that the proposed method can achieve relatively high accuracy of ice water classification results. And for the first case, the average wind speed over the open water region is around 70 meters per second. Wind-wrapped open water and multi-year ice-covered areas have very similar backscattering intensities, especially on co-polarized star images. For this case, our method reduces the number of misclassification of sea ice as open water, especially in the far range. Moreover, open water is rarely classified as sea ice in the near range. The reason for that comes from that sea ice and open water are related to different surface scattering mechanism. The former is associated with volume scattering, and the latter corresponds to surface scattering. Therefore, the selected polarimetric features can be used to well discriminate sea ice and open water. In the second case, the average wind speed over open water area is around 8 meters per second. In this complicated marginal ice dome, sea ice and open water have comparable HV-polarized backscattering. Figure H shows the grade classification results derived from experiment 3 with the accuracy of about 98%. Compared to the other two experiments, the significant improvement obtained by experiment 3 implies that polarimetric features should be taken into account in the ice water classification. The SAR sinks in the third case are obtained in the melting season, so we can see quite a few ice flows in the SAR images. These ice flows manifest various morphology features due to the combined action of wind waves and currents. The classification map of experiment 3 is more consistent with the reference map and the SAR image, with the accuracy of about 91%. This case indicates that the proposed method has potential to well identify sea ice and open water even in the melting season. In the last case, due to the high resolution of quad-pole SAR image, several long, narrow sea ice leads are clearly visible in ice pack regions with very low radar backscattering. The identification of sea ice leads is very important because very small changes in these areas have the potential to induce large temperature fluctuations in atmospheric boundary layer. In this case, backscatters from several ice-covered regions are very similar to backscatters from sea ice leads, which indicates that the surface scattering is possibly dominant in these areas. Sea ice in these regions are misclassified as open water, even for the HA alpha Wishart classifier. In contrast, our method identifies sea ice and leads very well and generates more reasonable classification results. Moreover, we can also observe pressure ridges in the SAR image, which identifies as bright linear features. In ridge covered areas, strong volume scattering occurs. It can be seen the experiments 1 and 2 misclassified several very short ice ridges as open water, but experiment 3 doesn't. And to sum up, we propose a physics-based and data-driven method to automatically classify sea ice and open water with high resolution from C-band RADARSAT-2 polarimetric SAR imagery based on random forest model. And the statistical validation results show that the overall sea ice and water classification accuracy can be improved by 5 to 10% when the optimal polarimetric features are involved in the model input. The proposed approach has capability of yielding satisfactory ice water classification over the complicated marginal ice dome in different seasons under different wind speeds. High resolution ice water classification maps clearly show that sea ice leads and their surroundings are also well separated. That's all. Thank you for your attention.
Thank you, Yiru. That was great. Thanks so much. It's time for a question. If anyone has one. I have one question. I wondered what other data can help you to clarify between these different systems, like if it is like a rough sea surface caused by wind, or is it like this pressure ridge or not? Yes. Will, do you want to add something to that? Or Yiru, do you want to answer this first? Will, is this related to what I just said, or do you want to?
It's different.
Different? Okay.
So go ahead with your question.
Okay, Yiru, is there any other data that could help you identify these ridges or the rough sea coastal wind better?
Actually, I think now there's only the in-institute observations can confirm the sea ice leads because the sea ice ridges, because this SAR imagery, the wide swath of hot pole SAR images is very small. It's about 25 kilometers, and now the other satellites, their resolution is very coarse, so the ice leads can't be these small ice ridges can't be identified. So we just identify the sea ice leads through visual interpretation.
Okay, thank you. Will, do you want to answer your question, please?
Can you hear me?
Yes.
So a practical question, Yiru, maybe you already said, but I missed it. Is your approach practical? Can it be used in operations? Can it be sent to the Marine Forecast Office in Montreal? Can they use it as opposed to doing manual analysis now? What is your thought about that?
Yes, for some, in some case, it can be, the cases showed here, we can see that it can generate a good performance on ice water classification. But for some case, it's still needs, but in some other cases, it's still need to be improved. For example, some which we didn't show here, that this method will still be affected by the incidence angle dependency. So I think this method still needs to be improved for operational use.
So in terms of application, though, do you think that marine forecasters can easily take your approach and adapt it? You've spent a long time to develop this methodology, so I just wonder, can it be given to somebody who's not expert in machine learning, and can they use this, or do you think it's too difficult for them?
Yeah, I think it's if I package the algorithm, the code, then it's very important. It's very easy to use this method without any expert knowledge. Mm-hmm. Anyone can use this just with one button. Press the button.
Okay, that's great. There's good potential then.
That is, like, I know of this app, it's called Ziku. There you can access like SAR data for the Arctic regions in Canada. And it also has this citizen science approach where people can add like their ice observations. I don't know if you're familiar with this, SIKU. And if that's something like you want to go towards, like a more like a, you could actually see them on your phone. It's my phone doesn't handle it very well, but
you mean the concepts marine forecasting project? Yeah. Yes, we're very familiar with that. It would be good if this could be taken into that sort of system.